Okay, got our recording on. Let's get going. So again, we're in 12. You might want to log into Pro or log into Replit if you want to work with any of the data today. We're going to talk about our first associative container sets, and then we're going to have a brief flyover on this thing called pairs and function objects or functional objects. This is kind of a early introduction, but we'll come back to those a little bit later. Quick announcements as always. We had our lab 11. Today's is optional. So if you want to just kind of reinforce what we go over today, as always, this lab 12, you can submit it anytime between now and the end of the semester. So it will replace your lowest lab grade or it will be dropped. If you don't do it, it'll be dropped as one of your lowest grades. So hopefully that gives you some flexibility. Big quiz coming. So not our material from today, but everything through 11. So you may want to review that stuff. And then, of course, Connect for next Tuesday. And I might have some more hints for you on Tuesday for folks who are still struggling on the last little bits of that. But hopefully everybody's not going to wait until Tuesday to start on that. So hopefully you can use some of your lab today to get that done. Now, in a little over a week, we will have a little over a week, almost 2 weeks actually. We'll have on lecture 16 our midterm. So I think that's the 13th of March, if I got that right. Yeah, it seems about right. So you got to be here in class. It's going to be online, open book, no help, obviously no AI. And you'll have a practice test probably by next weekend. So the weekend before it, try to get your practice test out for it like usual. And you'll want to kind of review. Don't forget quiz 4 because that's going to help you know the kind of questions are on there. Okay. This is not a hard midterm. This I'll let you in on a little secret. It's like this is like the last exam I haven't rewritten since COVID, right? Since pre-COVID, I've been meaning to. It's still a lot of multiple choice, some essays. I'll probably upgrade a few questions, and you'll see all that in the practice exam. But this should not blow you up, right? So just if you know your quiz material, I think this stuff should be relatively straightforward for you to do, and you'll have about 170 minutes on that one. Okay, so don't forget about that. Please set your alarms. Don't forget to come to class because otherwise you get a 0. Now, well, I'll just leave it at that for now. And if anybody has any questions, they can kind of ask me. And that's worth 22.5% of your grade. So that's a big one. So don't miss out on that one. Quick review stuff. So remember reading files. The easiest way to do this is to have a IF stream operator or a variable and a word that we can load stuff in and use this pattern. This is the easiest one. And we didn't talk about it, but you can even load multiple variables. You can say my file less than word, right? Or some other variable. So you can stack these things up if you want to read 3 things at a time inside of that while loop. So this is the cleanest way I've seen for reading things that are delineated with white space, which is tabs, space characters, end of line characters, all that stuff. Okay, and then of course we want to close our file. So we'll be reading a lot of files just to work with some data. Always makes things a little more interesting. We could test for EOF, but there are some behaviorisms with this where if you have blanks at the end of your file, you might get some duplicate data. So this kind of works, but it's prone to bugs and is more fragile than the previous approach we looked at. Okay, but that is also another way to go with that. Talked about our range-based for loop. Remember that we can say vector int or we can say auto because, or sorry, we could say int or we could say auto because auto figures out what's inside of that type. So whenever we use auto, there has to be some clearly defined type that gives it a hint. As long as it gets a hint, the compiler will fill that in with the right stuff, which is really kind of nice to do. Okay. So by default, we get a copy of that unless we put the ampersand in there. So that was a really key insight, and I guarantee this is going to trip some of you up this semester. It catches me. It's like I do an auto for loop and I want to change that item and then I forget, oh, it's not the real item. It's a copy of the item. So printing, that's an okay way to go, and it works for everything, right? But if I want to change something, Or first off, if I just wanted to go fast, I do const auto ampersand, and now it's going to go faster because it's a reference, but it's not changeable. So that's a really safe way to print something really fast, which is a little weird, I know. But if we plan on changing it, then we gotta do the auto ampersand, okay? And now we're actually modifying the vector. So that's a super important thing to remember when you're iterating through really large amounts of stuff. So, okay. And then sorting, this was the really cool thing we talked about last time. We're going to see a little bit more of this going forward, this idea of passing a function somehow into another function so we can call it. So here we're literally passing in a pointer. The name of a function is really a pointer to the function. And so if we know what kind of function we need to write to be compatible with sort, and this just happens to be one of those compatible functions, then we can let it do the calling, okay? So the pattern is usually, I'm going to give you a little piece of logic and you're going to apply it many, many, many times, right? So our sorting function applies that comparison. And that's a pretty common pattern out in the world, regardless of what language you're working in. It's a very powerful one that allows us to reuse more general code, okay? So today we're going to talk about sets, which is just part of our associative containers, and a slight variation on them called multisets. Now, for those of you who took algorithms, you're going to feel hopefully a little familiarity with this because it is actually a binary search tree. So very often sets are implemented as a binary search tree underneath the surface. And that's in particular when it's an ordered set. So for those of you who remember binary search trees, it's a great way of actually getting something sorted in order. So we can find things like words in a dictionary or, some number in a set of numbers. So we'll look at that. And we're going to look at this new animal called functional or function objects. This is some crazy stuff. Have you ever seen those sponges that you pour water on and they just sort of turn into a sponge? That's what I feel like these things are, right? Some of what we can do with these things are pretty crazy. So I will show you that one here. And it won't take you a lot to recognize some of the stuff that we're doing there. Now, it turns out that the library called functional includes a lot of these objects. So there's a lot of these written for us ahead of time. Think of these as those mini functions we played with last time, little tiny atomic functions that do things. So the functional library includes some really useful ones. I want to show you an example of how we would use those. But eventually we're going to write our own functional objects in a couple weeks later on in the semester. Okay, so let's review the bigger picture. We have looked at all of our sequential containers. We are now jumping into the associative ones. So set is really kind of the easiest one. You'll recognize it pretty quickly. Map is sort of a grown-up version of set. It includes not only a key, but actually a key value pair. So you can think of just a key as like letters, in a game of Scrabble, right? Key value pairs is like a word and then the definition of the word in a dictionary, okay? So we'll look at kind of both of these. Today, we're really just going to focus on the set and the multi-set because they're kind of part of the same kind of piece of logic, right? So today is just a set and a multi-set. That's unique keys or duplicate keys, right? And they're going to be ordered. So all of these up here are ordered, and I'll show you what that means. And although we won't spend a lot of time in the unordered world, because once you know what ordered is, you'll know what unordered is. That's going to be kind of all the rest of our containers, okay? So this is our binary search tree. Again, for those of you who remember that from algorithms class, and for those of you who are going to take algorithms class, you might go, yeah, I'd really rather use this than have to write it from scratch, because you Comp 220 folks probably remember how complicated that was. You may also remember symbol tables. So when we say we want an unordered set, again, Comp 220 or algorithms folks, that's a hash table or a symbol table, okay? So those were some two, 3, 4 lectures we covered and did a homework on all that stuff. Here we have them all ready for us, done in C++, and we just get to use them and they're all optimized. So that's kind of nice to be able to do. So let's kind of dive into these, and I've kind of created this reference code file. You can look at it in either one of these platforms, but basically it just throws all of the code into one playground, and so you can kind of go back to that if you want, but we'll kind of attack it in smaller pieces. So what do you use these associative collections for? So typical things would be where you have a unique thing that we can look up, a social security number, an email, a username, student ID, or maybe even words like, hey, I'm playing Scrabble. Is that really a word? Let me see if that's in the dictionary, okay? So those are our keys. They are usually unique, but they don't always have to be unique. It would be a bad thing if your social security number was the same as somebody else's, but you could kind of see how maybe your first name or even your last name might be the same as somebody else's. So sometimes we want unique keys. Sometimes we have no choice. We're going to end up having duplicates. Okay. So sets require unique keys. So that would be more like a social security number or a login email. We don't want more than one person on Facebook with the same login email, right? That's just not going to work, okay? And increasingly, our usernames are our login emails or something unique as well, right? We used to be able to have any username we want, but increasingly, usernames have to be unique. So that's what we're going to be putting in our sets. And the other thing about sets we're going to find out is they are ordered. So the ones that we're going to be working with are going to always be actively maintaining order underneath the surface. So as users of these associative containers, we don't want to have to worry how you keep things in order. We just want to put more things in the set and have it constantly, like a little watcher, making sure that it's organizing things underneath the surface. Now, again, those of you who remember binary search trees might remember that when we insert a key, there's a lot of work going on underneath the surface to figure out where to insert that thing in the tree. So here with sets, we don't have to even worry about that stuff. It just happens, and anytime we want, we can print out the keys in sorted order, right? The whole time, right? And in theory, it all happens efficiently. So this isn't how we actually see it happening under the surface, but the idea is if I insert a B, it immediately goes into a place where I can kind of print things out in order. It's not like it sorts them later on. It's going to pretty much ensure that it gets put into a good place, okay? So there's our F, etc., okay, and our D, okay? So we're going to maintain order, or we're going to allow these things to maintain order if we're working with our standard set. Now, if we decide that we want to work with an unordered set, that's going to be something different. It's going to be called an unordered set, okay? So here's an example of unordered keys. I know I'm probably kind of, beating this one to death, right? So I could have unordered keys, and if I try to insert the 4 again, it's really just going to replace the existing 4. So you might be surprised there's not an error sometimes when you do that. It's a silent error. Maybe if you might think you added an extra one, but if we have no duplicates, then it's just gonna, ignore you essentially, okay? Now over here we have ordered keys, and so when we insert them, in theory, they're somehow getting put in the correct location. And my animation here doesn't do it justice, but here again, even though they're ordered, we still don't allow duplicates in this scenario. So a extra 3 in there is just gonna be ignored effectively, okay? So here's another way of thinking about this. So if I create set int my set, no matter how or what order I insert them in there, it's going to automatically maintain that for me, okay? So the 5 just replaces the existing 5, the 1 replaces the 1, okay? So there's a little bit of redundancy between those two slides, so apologies about that, okay? And there's our duplicate item, okay? So underneath, yes, it is a binary search tree. There's something at the root, and then the lesser things go to the left, and the bigger things go to the right, and that tree continues on and on and on. We won't get into all of that mess, but that's good to remember that that's generally how those things are done. So let's look at more comprehensive set of the code. So set int SA equals 2143650. Okay. So that's our initial values. And even though I see these kind of listed here in random order, it's going to immediately construct that set and put them in sorted order. Okay. And the default is ascending order. Okay. So it's got to be integers, right? Now, here's some interesting sauce. Notice that in addition to this template parameter, I've thrown in a different data type. So this is a data type. It's a class name called greater. And it's actually kind of like int. So int is kind of a data type. We can put class names in our template parameters, but it actually ends up having this other template inside of it. So it's like a vector of vector. So it's a type with another subtype. Okay, so you might look at that and go, I don't know what that is. So we'll talk about that here in just a second. But essentially, that is how we change the behavior of our set for all times. Once we create SD, set descending, it is always going to organize those numbers in descending order when I insert them. Okay. So if I insert a -1, then that thing should automatically end up at the end of SD because we created SD in this particular fashion. Okay. So it's not like I have to say insert it at the beginning or insert it at the end. It's always working silently in the background to make those things ordered for us. Okay. Now, the other thing about sets is we can't pull out something with square brackets or an at. There's nothing to pull out. I can't say go to position 0 or go to position 1. They don't really work that way, okay? So I can only really do something via our iterators or via our range-based for loop. So I can say for auto x colon s, so that's getting a copy of each thing in the S set. Notice I don't have my ampersand there, so X is going to be a copy, okay? I could do this. Could go back to that kind of messy version. Auto iterator equals S dot begin. Continue while iterator isn't the bumper, right? Increment the iterator. And then dereference, even though that's an overloaded star, right? It's an overloaded operator. We're just saying, hey, go to where that iterator is pointing and give us what's there, okay? Definitely a little more of a messy thing to do. Most of us would probably prefer to do something like this up here, okay? Okay, so let's see if we can construct a set real quick. And notice that when we list the numbers, just list them in any random order, right? When you put your numbers between the curly braces, just use random order for that. And then go ahead and print them out using a range-based for loop. So this is a good warm-up, okay? And you should notice that those things get printed in a certain order. And if you want to modify that order, go ahead and alter your creation parameters on your set to just convince yourself that you can force it to change its behavior, okay? So that's the extra parameters. So I'll kind of give this to you in pieces, but I would suggest you give this a try. Set, and you might need to pound include set up top. I can't remember if I did that for you, but set, name of variable, and I think the equals here is optional. So you could say equals, curly braces, any random order. Okay, and that's going to be ascending unless we change that behavior. Okay. And I'm going to go back and look at my program IZ thing real quick while you guys are doing that. I'm not going to change my, whoa, sorry. There we go. But yeah, most of that stuff's in there. So there's our set, right? So you can kind of put whatever you want in there. And then here's our range-based for loop, okay? So pretty straightforward, okay? So this could be words, it could be integers, it could be any data type. It could be instances of some class that we have, right? So these could be constructors for cards, for example. You remember our deck of cards thing. We could have cards, right? Cards 8, right? And cards could be the name of a constructor for a class. And now the thing that we're putting in our set would have to be of card type, okay? So sets can be anything, instances of a class or fundamental data types like int, float, char, etc. Okay? So anything we want to put in there should work just fine. We just got to make sure that type is the right type. Okay. And then there's our iterator. Okay. Now, you could, if you wanted to print this in reverse order, you don't have to construct it in the using the greater than. You could just iterate backwards. So some of you experimented with this last week. You could say, my set dot begin while not equal to my set r begin, sorry, r begin while not equal to r end. That's a kind of clever way to iterate backwards without all the messiness, okay? But we could also just pass in that greater. Okay. So let's talk just briefly about what these functional objects are. And you can kind of look at this library. So CPP reference is a little bit ugly sometimes, as you can see. But here's the functional library. You can kind of see that the URL reinforces that's what we're looking at. And there's a whole bunch of things in here, right? Greater, this is what we're looking at right now, part of the ranges sub namespace. And we won't go through all of these things, but there's a lot of stuff in there. So why would we use these things? Well, they're sort of those little sponges, right? That you pour water on and they turn into functions. So that is just a data type. It's not a thing. There's no function there. Greater, less than int is just a type, like vecint, right? So think of vector int is a type. So what we're saying is, hey, here's the data type. So how does that get turned into a function that can be used inside of the constructor for our set? So SD is going to call its constructor and feed it this stuff. So how does it turn that thing into a function? And that's what we call a function object or a functional object. These classes have an overload for a symbol we haven't really looked at yet, the function symbol. So we can make an instance of a class act as if it is a function. And that capability in the class allows us to pour in this dried up sponge here and let the set constructor kind of pour water on it and turn it into a function, if you want to think of it that way, okay? So there's a whole bunch of these pre-made functional objects out there, and we could write our own, but they're just like this: template, greater, overload, function, return whether or not A is greater than B. That's it. So let's think about that for a second. So greater is a class. In this case, it says struct, but that's really the same as a class. We just don't have to say public right there, right? So we could say class greater public, and it would be the same thing. And then we say, hey, whatever type you give me, that's what I'm going to return to you, okay? So I'm going to return, either Boolean or I'm going to return some type. This says integer. I don't know why I've got that a little bit off there. But essentially the idea is we are overloading and having this instance of the class behave as if it is a function, right? It's like, wow, I can create an instance of a class and make it look like a function. And we're going to do a lot more of that. But it basically means we could do this: greater int myinst x int x myinst 3 comma 4. So I think my logic here is flawed. It should say this should be a ternary operator. If A is greater than B, return A, otherwise return B. So that's a little typo on my part. So that's all that's happening. Myinst is an instance of this weird class that allows us to treat it as if it's a function and give it some arguments. And it kind of goes, oh, all right, I know what to do with that. And so this is that sponge, right? So we can pour the data type, which is a templated class type, into another templated set. And the set function constructor will do exactly this. It'll create an instance of our function in the constructor, call it as a part of its sorting algorithm, okay? Some pretty crazy stuff, but it is really very much what we were talking about in our last lecture. We've just found a clever way to feed the function as a dried up sponge into the template parameter here, okay? Because otherwise, where would we kind of sneak that thing in there, right? So That's a pretty cool thing. So we call those functional objects. Sometimes I refer to them as function objects, but functional objects. And we can write our own, and we will write our own versions of that a little bit later in the semester. But for now, we're just going to really use it to kind of change the ordering of our associative containers, okay? Very cryptic if you don't know what it's doing. And don't worry if you don't kind of totally grok that, because we'll come back to it. But otherwise, we just have some nice methods. We have no at or square brackets for sets. We will see that we do have them for maps, but we don't have them for sets, right? But otherwise, most of these things are identical for sets and maps, and for other containers as well, right? So the other associative containers all support these except for sets. That's only in the map thing. And we'll see that on Tuesday, okay? And we have some capacity methods, the usual size stuff. Is it empty, true or false? And we can do our typical iterator stuff, right? Begin, end, or reverse begin, reverse end, okay? So we could do some erasing or editing. We won't dig into these too deeply, but we will definitely be inserting stuff. So we want to put more items, more keys into our set. We probably won't look at the in place. Sorry, I don't know what that is over there. There's a little bit of a typo there, but we'll come back to the insert here in just a second, okay? But that's just sort of a look at that. Now, if I want to know whether there's a particular key in my set, think of it like playing Scrabble. Hey, is that a word or is that not a word? We want to see how many times that word is in the set. It's going to be really 0 or 1 for our set with unique keys. But if it was a set with duplicate keys, then it could be any number, right? So think of a histogram, right? A set is a really great way to build a histogram of words in a story. I think I've told this story before in my other classes, but UC Santa Cruz computer science, one of the labs is to come up with a histogram of all the words in Shakespeare's sonnet, right? So, you know, what are all the words that Shakespeare likes to use, and what's Shakespeare's most favorite word, you know? Well, the set is a perfect way to do that, and the count method tells us how many times we saw a particular word, okay? We can also do things like go searching for words, look for the lower bound, upper bound, equal range. And again, folks from Comp 220 might remember that our binary search tree supports these things. So this is a great example of how an underlying data structure is peeking through the methods a little bit, what we call the interface of this particular set class, okay, which is something that just kind of happens. Now, if we do insert something, we kind of want to know, did it get inserted? So I can say auto P equals S dot insert 25. Now, maybe the 25 didn't really get inserted because it was already there. So the insert method gives us back something called a pair, okay? Now, this is somewhat cryptic, and you're not going to be tested on this really. We'll learn more about pairs in the near future. A pair comes with two parts. It's like two things in a box, okay? So the first thing is what we call an iterator. It just points to the answer. And the second thing is, did it actually happen? True or false? And you guys know me, I like to always return a true or false from action functions like that, like our self-driving car. Like, did the car turn on? Did it accelerate? So if I say if P dot second equals true, so P is an instance of this pair class, and its property values are first and second. Now, you wouldn't know that unless you studied the pair, and we haven't studied the pair yet. But first and second are its data members. So notice that I'm not using an arrow. I'm just saying P dot second. Sorry for my long typing here. If that is equivalent to true, then we know it's in there, right? We actually did insert. Otherwise, something failed, okay? And notice what I did here. I said, you just inserted, and it gives me the iterator, right? That's pointing to the thing, right? So I say P dot first dereference. I'm dereferencing the iterator that's stored over here. Think of it as a pointer pointing to what's inside of my set. Okay. So if my set was like this big long thing over here with a bunch of keys in it, right? And I inserted it, it's like, yeah, that's where it is. You just put it and it's right over there. Okay. So let me give you a moment without all the red stuff to think about that, right? A pair, the first thing is an iterator telling us where to go look for something, and the second is a true or false value, okay? If it's false, then this is going to be null, right? So if it's true, then of course we want to follow that iterator, okay? So pairs are a little bit cryptic. We'll come back to those, but that's one way to just figure out whether we were successful with that. And there's all sorts of games that we can play, and we'll do this here in a practice problem here in just a second. So if I say, hey, what is the lower bound of something that of a 3? Like even if there's no 3 in here, what comes closest to a 3? Okay. So the answer to that question is going to be whatever is greater than or equal to 3. That's what a lower bound means, which is a little bit confusing, I guess. And the upper bound is going to be what's greater than that value. Okay. Kind of a strange thing, but the upper bound there would give us a 7 if we said, what's the upper bound on the 6? Okay. So again, not a critical thing that you guys memorize all these rules, but we want to be able to think about, asking questions of our set. Okay. So we can kind of iterate to find that thing, or we can call the function. But that's essentially what that thing is doing. For iter equals lower, continual iter is not equal to upper. That's going to give me now the range of things between there, right? Okay, so this is one way of finding out, hey, what's between these two things in the set, okay? Because sets are ordered, right? So it makes sense to ask for a range of things, okay? So this is just one way of getting a range. So let's kind of do some stuff with some data. So there's a whole lot of words that start with the letter A in the dictionary. So let's kind of open up a file, because that's something we should all know how to do as advanced coders. So we're going to use a file stream operator, and then we're going to store each thing from the file in our set, okay? We'll close the file, and then we're going to print out the entire set, okay? And then if you want an extra challenge, see if you can print out words within a certain range, okay? Like from ADO to adopts, right? So using our upper lower bound. So let's just take a peek at this. I'll let you guys code this up so I don't mess up my sample here. Oh, I thought I was logged in. Oh, come on now. All right, let's see if I can actually pull this off. So now I got kicked out. But you guys jump in if you want to actually do this. I'll pull up the sample code here and just actually let me try this. Oh, no. Sign in. That's what I need. It's new. Always surprised if I get it right the first time. There we go. Okay. So we want to create our set, right? So it's going to be set string, whatever you want to call it, right? So the name of your set can be whatever you want. Okay. And then we're going to, we already opened our A words. So we got a whole lot of A words over here, right? So these are all of the A words in a pretty standard dictionary. And that's pretty comprehensive, actually. I think that comes from Words with Friends originally. And then we'll go ahead and read those things in, right? So we want to insert them into the set. So it's really just whatever you called your set dot insert. Close the file, and then you can kind of use an auto range for loop to print that thing out. So let me put some code up here so you guys can do it, right? So there's our set, our insert, our close, and our range-based for loop, okay? And if you want to add const auto ampersand s, it will go faster. You might not feel that it's going faster, but you could probably time it. And then if you want to print out a range of words between this upper and lower bound, right? We can say, get the lower iterator. So this is the word at that lower iterator. Dereference the lower iterator from the lower bound. That's just saying, hey, that's the word that's closest. And that's the upper bound on adopts. That's the what's at the iter, the upper. And then I can go from one to the other and print out every word in between, okay? And this is kind of probably, well, one way that Google might say, you know, oh, I don't know that word you typed, but maybe I can get the closest thing to it and make some suggestions, okay? We've all done that where we typo a word when we're searching and then it says, maybe this is what you want. So that's one of the ways we can actually get a match for that, okay? It's kind of looking at the things that are in sorted order and pulling those out, okay? And so again, if you remember your binary search trees, that's going to be n log n. That's pretty fast, right? For searching, for printing out everything, right? We want to print out everything in that binary search tree, but it's going to be log n if we just want to find one thing, okay, on average, okay. Now, one of the hardest lessons we can learn, and we need to learn this for both sets and for maps, which are coming up next week, is does it exist in the set? So the best way to do that is to count how many of them there are, right? So int my count equals set count. We're looking for a -1. Is there a -1 up here somewhere? Okay. So if that count is 0, then there isn't one, right? Otherwise, there is. Okay. So we could say that way. We could say if s.count -1 is equivalent to 1, then yes, that's a word, right? Or that's in the set, right? Okay. So right now we're dealing with integers, but it could be words, it could be instances of a deck of cards, it could be an instance of a person's IRS records, right? So all of that stuff works depending on the template parameter of our set. Okay. So if I want to find it, in other words, get a pointer to it via an iterator, I can say auto, or I could say set :iterator, right? So that could be auto right there. Iter equals s.find3. So why would I want to find the 3? If I know it's a 3, why do I need to find it? Well, if it was an instance of Jeff Yates's IRS records, it's got a whole lot more maybe than just the 3. It might have a whole instance of other things in there, okay? So sometimes we want to get an iterator that points to the thing we're looking for. It's not really a pointer, but it's sort of acting like a pointer, right? So if the iter that we get back is not the bumper, the end stop, then we can dereference it and see what's there, okay? And very likely, in this case, it's going to be a 3, right? Because we know it's a pretty simple data type there, okay? Otherwise, we can say, hey, that thing is not there, okay? So that's a different way to actually do it. But the count is kind of a lot less painful, okay? If I just want to know if it's there, just check the count, okay? And then you can always try to do the find, but it's really not that necessary. So when we do our big Facebook homework, some folks will be using the find, but you can use the count as well, okay? So that's all we're really doing if we shorten that up a little bit. So it's okay to think of these things as pointers. They're just masquerading as pointers. So here's another database with about 9,000 words that start with lowercase b or uppercase b. So we're going to do something really similar. We're going to store it in a set. We're going to ask the user for a word, and we're going to try to find the nearest word to that word. So this is kind of an actual interesting working program. So if we find it, we want to print out the word and say, yeah, I've got it. Or we want to say, oh, maybe you meant such and such, upper or lower bound, okay? So let's look at the code. You guys can probably jump in and start this right off the bat if you want. So there's our giant dictionary of words. Okay. So our set is opening. So all we need you to do here, so we're going through and loading these things in. Okay. So if you, let's see, oh, so this is where we inserted it in the set. And this is where we're asking the user, what word would you like? And then we're going to see if it's actually in the set. So here's where I'll switch to our code here to help you guys. So first we want to find that thing, right? So we can say if my set.count of word is equal to 1, this is the easy way to do it. Then we know that's a word, okay? Otherwise, it's not there, but let's see if we can be helpful and print out the upper bound of that word. So what's at my set upper bound is an iterator, right? So what's the upper bound of that? What's the lower bound of that? So that gives me 2 words that I can suggest, okay? And then we can just loop around and do that whole thing over and over again, okay? So that's starting to get kind of useful, especially if you have a really big dictionary. So here I just have the B's, but our giant dictionary is about 140,000 words. So it's a lot bigger than that right there. Okay. So again, think of upper bound and lower bound as giving you a pointer that we have to dereference, but it's not a pointer. It's an iterator that's been overloaded to act like a pointer, okay? So let's just look at multiset, and I think that's going to turn us into the final turn here. So multiset comes from the set. So you just got to say include set. But when we create a variable, we use the word multiset. I should have used lowercase m. That's very misleading. Trying to do better about that. So that should be a lowercase m. So multiset is a set that supports duplicate values. It's still sorted, right? It's still going to maintain order, ascending or descending, but it's going to allow us to insert lots of duplicates, okay? So here's us putting in lots and lots of duplicates, right? So if you remember, apologies to folks who haven't taken algorithms yet, but binary search trees can store duplicates. We just had to decide whether we support that or not, right? And we store them either on the left side or the right side, right? When we do our comparison. But here we see kind of that implementation in a multiset, right? So if we want to do something, we're going to try to do something useful. Let's try to find a median value. This is actually a computationally expensive thing to do. In order to find a median value, you kind of sort of need to partially sort your data or sort it just enough to find that median value. Here, we're going to do it in a maybe not the most efficient way, but one way to do it is store it in a set, right? And then we're going to find the middle value. Now, technically speaking, for even numbers of items, we'd need to average the pair in the middle, but we're just going to cheat today and divide the space in half. So, or we'll just use odd numbers today to make things easier, okay? So the size of your multiset divided by 2 plus 1 should get you to your median value if we're dealing with an odd number of items, okay? And that's what we're going to do just to simplify our lives a little bit. So basically, our set does the sorting, and we got to figure out how do I iterate through half of the items, okay? So that's, as you might expect, we're going to use our iterator. So let's take a look at the code for that, okay? So there's our data, right? Obviously not in order. It's a beautiful thing when the set just takes care of all that for us, right? Create an empty set, fill it up. I'll show you the code here in a second. And then print out the contents. And we're going to need to keep this variable kind of set to 0 and then increment as we iterate. So I'll show you what I mean in our solution code here. But so we open the file, create the set, insert some values, close the file, print them out just to, so we can see them. And we know that the median value should be at about halfway through. So we'll set some kind of counter to 0 and post increment it after every time we iterate, right? So we say if the count is equal to size over 2, then we know that the median value is at location I, okay? Which should end up being count, right? So, or not, sorry, I is not the count. Sorry, back me up. I is not the count. I is actually from the set. It's a value, okay? The count is here because we don't have a counter in our range-based for loop. So apologies for that confusion there. We need to create the count variable so we can keep track of how far we've traveled, okay? So after the loop is done, right, we know that that the MSET count of, oh, FYI, 1 occurs MSET 1 times in the, so how many times it occurs. But we can find the position of it, sorry, we can find the position via count, and we can print it out on the fly. And probably we should break out of the loop after we find it, right? So I really butchered that example pretty badly there. Okay, but I think you can try this and see it'll work, but we could probably make a slightly more optimal version of it if we wanted to. Okay. Okay, but those are just some examples of the set and the multi-set, okay? And it's a very efficient way to actually pull stuff out, okay? That's really all we got today. So I didn't want to try to cram in a whole other topic and run out of time. So we're going to kind of give you some time back today. But our optional lab today here is just sort of going through and loading some words from the file and figuring out whether something has a word, okay? So we want to pass in the file name to a function, have the function load that thing back up, and then give us a set, okay? So our function is going to load the words and give us back a set with all the words. And then we want to have a separate function where we pass in, notice what we're doing here. This is a const ampersand reference. So we're saying, hey, here's your words, but you are not allowed to change that set. I just need to know whether you found the word in the set, okay? So this is a very typical thing to do, is make that set const ampersand. So we're not making a copy of it, so we're not wasting memory, and we're not, doing things slowly, but we give the hasword function the access to that information. So that's a really efficient way to pass in a really big piece of data. And then, hey, tell me whether or not you found that thing, okay? So that's really all we got going. Let me make sure that this Program IZ Pro example has got everything you need. So you should notice this is the large dictionary. So we got, what is it? 170,000. So it's a little bigger than I remember. Okay. And so you're just going to need to kind of fill in, write the functions, right? So main, I'm pretty sure, is done for you, right? So I don't think you need to do anything in main. It's just a matter of implementing your prototypes down here that match these guys up here. Okay. So that is it. That is optional. And I release you to do what you need to do. And I hope you guys have a good weekend. I'll see you on Tuesday. Thanks.